with the next few slides. So imagine we are dealing with a new toy statistical model, which contains 3 parameters. So the statistical model is representing y as a sum of x1, x2, and a random variable, which is like a noise, like represent a noise here. And then x1 and x2, they are both given normal priors, standard normal priors, and this random noise is given a normal prior with some known variance. So again, we think that like we have observed a single data point from such statistical model, and same as I've told before, we can sometimes derive conditional updaters for Bayesian sampling, for posterior Hmsc NIP sampling. And in this case, we can derive them in closed form. So given that like x1 and x2 are symmetric in such statistical model, it's effectively that both of them are going to have the same structure. Both conditional updaters for x1 and x2 are going to have the same structure. And both of them are normal distributions with mean and variance given through these expressions. So how does it go then, the Gibbs sampling in practice? So let's start from origin, so from 0, 0. And this is the first step which Gibbs sampler makes. So it consists of 2 parts. So the first part is updating x1 conditional on x2 data and theta, and then and sigma. And then the second part is updating x2 conditional on x1 data and sigma. So the first step is highlighted, is represented by red line here. The second step is represented by the blue line here. And after we made the cycle of Gibbs iteration of Gibbs steps, we are in that small black dot. Okay. Oh yeah, and for now we will gonna consider the example where the sigma equals 1. So then we can make a second step. Yes. So again we have the red. We make a second cycle, second Gibbs cycle. So again, the first updater is represented by the red line, and the second updater is represented by blue line. So as we're doing Gibbs, component-wise Gibbs, like the reds are always going only along the x1, while keeping all the other coordinates, which is just x2 in this case, constant. While while the updater for x2, they adjust the x2, while keeping x1 and all other potential model parameters constant. And we can run it a bit longer, and this would produce us the samples from our posterior distribution, which is posterior distribution itself is visualized by these contour lines. So now we have only 20 of them, and maybe that's not enough for this problem to properly summarize the posterior distribution, because we typically want it to be kind of fully covering the probable regions. But let's first highlight what are the potential issues which this Gibbs sampling can encounter. So as I mentioned before, one of the drawbacks of MCMC is that like there is inevitably autocorrelation. Okay, almost always there is autocorrelation in the samples which it produces. And this becomes more evident once we consider that like the same problem, but like now with a different value of sigma. So now once we decrease the sigma, the true posterior, is starting to get more narrow and long. So kind of it's starting getting more narrow. So now, since we are only traversing this posterior along the coordinates, so along x1 and along x2, we cannot so well explore the posterior with a few steps, because if we start in one edge of the posterior, we would necessarily need to go something like this kind of ladder, well, in perfect case, to reach the other side of posterior. While in practice, we're going to kind of go by stochastic ladder, so going sometimes back and sometimes down. And if we kind of would start studying this problem in a bit more detail, this behavior is going to be more and more this annoying behavior is going to be more and more pronounced once the sigma start decreasing further. So what can we do here? As I said, we can do some more sampling. So maybe we can increase the thin here. So now instead of like recording every sample after the single cycle of Gibbs updater, we are doing 5 cycles of Gibbs updater before recording the single sample. So we can see all these updates like by red and blue lines as before. And now it's a bit difficult to see the dots. So let's see the dots themselves. All the dots. So we can see the dots themselves, and now they are spread quite well, relatively evenly for this small number of dots across the posterior. But apparently, the cost of that is that instead of like 20 cycles of Gibbs sampler, we had to run basically 20 times 5 equals 100 cycles of Gibbs sampler. Therefore, the required time to run those is 5 times larger. But it is exactly the number of thinning times larger than we would record every sample after each Gibbs cycle. Okay, then I also mentioned another problem, which was the potential so-called transient state of the MCMC chains. And here we can see it like if we start somewhere far away from the region which is supported in the posterior, we can first kind of traverse in other regions which are not supported by the posterior. And well, in this case, this traversion doesn't take too much time. If we would increase sigma further, it would be more and more time consuming. And therefore, once we run a finite length chains, this initial transient state, it can be detrimental for the quality of our posterior. Thus, the general approach which is taken here is to fit several chains. So something which also was talking about when he was presenting the topic of checking the convergence of Hmsc. So we can throw several chains over this like region. So and then see like once they kind of start in getting into the same region, no matter whether they start, no matter where exactly they start. Based on that, we can then cut the original part of each chain in such a way that like we don't take those samples into account because those were far away from the posterior, and just basically serve the purpose of exploring the landscape of posterior distribution. So one last thing to remind here is that like if we would run the block updater in this case, it would completely remove the autocorrelation between X1 and X2 because it would just directly sample from this target bivariate distribution. Okay, like do we have questions to this example? Or everything is clear? Or maybe opposite, nothing is clear. Also seems like nothing in the chat, but let's make some questionnaire first before proceeding. So would those of you who are present in the audience, in the auditory, raise their hands who has ever developed a Gibbs sampler yourself before? Well, couple people, 3 people, nice, 4 people, yeah. So for those of you who haven't done that, how kind of clean the concept seems to you at this moment? So would those of you kind of clear with this Gibbs sampling example raise your hands? I mean, the one which I presented. Okay, so maybe some questions from those people who are not clear with this example. So what is unclear exactly, or it's just like statistics and it's boring and so on? I mean, don't be shy. Like it's a course, and like the target here is to learn. So okay, we have Professor and his comment. Well, that's exactly going to be the topic to which I am going to switch next. And therefore, maybe I will take the liberty to answer your question in my next few slides. Yes, Carlos? Okay. It's complicated to make a computer. And then we have to produce. Why is it complicated? Why are there possible ways to calculate the procedure? And so far, this is the best one. I'm not saying that like this is the best one. Wait. Yeah, well, I would say like maybe it's one of the, I mean, it is probably the most common way to handle Bayesian model fitting via doing MCMC to get the posterior distribution or to approximate the posterior distribution using samples from that. There are other techniques. For example, variational Bayes is some technique which is similar to what Sarah Tuskin was presenting yesterday. So kind of approximating the posterior distribution of the latent factors in her case, like latent variables in her case, with within some tractable family, and then running an optimization problem over this parameterization of this approximation family together with other model parameters in order to find. So in order to convert to the Bayesian learning problem into an optimization problem in this kind of expanded parametric space, variational expanded space. There are also techniques which relate to MCMC, but which are not of such sequential nature. So those would be, for example, some particle filtering methods. But I would say, and I'm quite confident about this statement, that all of them, they are well, in general, they are less popular. They have their usage in, because we're doing chain, like to get, yes, we're going in chains. It's sequential because we're going in chains, and therefore also the name Markov chain Monte Carlo. So instead of like doing Monte Carlo sampling, which can be done, well, each sample at a time, each sample kind of independently from others, we need to run this Markov chain over the posterior in order to acquire samples from it, which we then would kind of thin in order to get independent samples, which we can say, okay, this is effectively independent Monte Carlo samples from the posterior. So I think I kind of listed 3 techniques, like variational Bayes, MCMC, like particle filtering. So there are different maybe combinations of those. But I would say we would like to avoid going into much detail here. Let's say that for now we are going to stick with MCMC sampling and particularly with Gibbs sampler. because if we think of MCMC sampling, there are also many techniques within this concept. Have I answered your question to more or less, or like if we would be smarter and if we would be better in numerical calculus, maybe we were going to be doing these models with just pen and paper, and then just doing some basic computations like with the computer. But unfortunately, we're not so good, and looks like no one in the world is so good to derive the posterior analytically or model kind of Hmsc type of model. Therefore, we are not we're not content with these approaches which are applicable to the very simplistic model, and which I've slightly highlight. Which I kind of demonstrated in these tutorial examples, where we can actually get the whole posterior in analytical form, and therefore do not need actually to get samples from that direct, maybe at all. So we have this multiple red circles here, each of which correspond to a block of parameters. So if we would, for example, write this Hmsc model into JAX or PAX, so this standard give sampler, this is exactly what they're going to be doing. So they're going to be cycling through each element of each block parameter. So let's say through each element of betas, and update it conditional on all other parameters being fixed to fixed to current value. So it's conceptually the same as what I presented with this two-dimensional case. So that we fix one parameter, we update the other one, we fix the first parameter. Sorry, we fix the second parameter, we update the first, we fix the first, update the second. But now we have not 2 parameters only, but maybe 10 parameters, 100 parameters, 1,000 parameters. So you iteratively cycle through all of them. Then there is this concept of block sampler, which can update maybe first 100 parameters conditional on all others. And this is what we're going to come into next slides. And yeah, well, that's the name of block sampler. So its benefit is that if we're doing that 100 parameters at once, instead of doing them one by one, we don't have any autocorrelation for these 100 parameters within them. We're doing them we're sampling them from the adjoint distribution, and therefore we're effectively doing Monte Carlo for these 100 parameters conditional on others. So we splitted the model. Sorry, first we split the task of updating of sampling all parameters or updating all parameters into simpler tasks of updating single parameters. But then we're kind of doing a step back in the sense that we are making groups of parameters which hopefully are easy to update together. So it's not that we're going to take these parameters at random. They're going to be actually well matching this directed acyclic graph of Hmsc, which corresponds to statistical formulation. And therefore, it's easier to derive these block conditional updaters. But okay, maybe we can proceed, unless others have questions to this part or to this two-dimensional example. Yeah, please go on. Could you speak, please, a bit louder?
This became some.
It's operating the random walk over the posterior. So the random walk in it is governed by the probability distribution. So in this case, posterior distribution. And it doesn't necessarily require it's in normalized form. So in general, like Hmc techniques require only the unnormalized posterior, so the one which we can calculate quite easily. So because it doesn't require that numerical integration which goes into the denominator. Then whether the chain is kind of guaranteed to converge. Well, it's guaranteed to converge after it has done infinite amount of steps. So it's not that like, for example, a convergence in some optimization problem where we know that like some algorithms given perfect precision, they converge into finite number of steps to optima. For example, conjugate gradient methods having this type of properties for quadratic problems. So in this sense, like we know that if we do enough samples, if we do enough Gibbs cycles or Hmc steps, we are gonna be very close to the true posterior. The problem is that like a priori, it's quite hard to predict how many steps we need. So that's why in the pipeline, there is this part of code where also is proposing to gradually increase the thinning or like the number of samples which is taken from the model in order to kind of diagnose where the when it's kind of saturating. Because if it's saturating, it means that like we're definitely not in the transient anymore. And well, it doesn't not necessarily say to us whether we're exploring the posterior proper like enough or not enough, but it is a necessary condition, and combined with other necessary conditions such like as Gelman-Rubin diagnostics, which also presented just today on the checking of convergence, it's it's again kind of not sufficient condition, but like it's a commonly applicable necessary condition, assuming that like you have started from some over dispersal distribution of your initial positions of the chains, which is typically guaranteed. Then this and once you have all good with the Gelman-Rubin diagnostics, you can say, okay, I have practical evidence that my chains have converged. Okay, but let's go further. And let's relate this simplistic example to how Gibbs sampling is done in Hmsc. So again, we have this directly acyclic graph, and we just initialize the parameters, these red parameters, by some random initialization. And then we proceed with our Gibbs cycle by updating the parameters once at a time, one block of parameters in time, where block of parameter is one black circle in this directly specific graph. So, for example, we start with updating parameter beta, conditional on all other being fixed. And because of the dependencies that this duck imposes, we don't actually need to take into account all the remaining parameters and all remaining all the data of the model once we update in beta. So what we actually need, we only need to account for the sources, which kind of directly goes to the beta, so kind of parents of the beta in terms of this graph, and its children, well, and also like the parents of its children. So in this case, we have this parameter beta highlighted by blue, And then we have all these nodes which we need to know in order to make conditional update for beta. And we proceed, for example, then we can do the update for gamma. Here's gamma. And here all the parameters we need to know in order to update gamma. And conditionally, only on these parameters, gamma updater is going to be equally well good as updater of all conditional all parameters in the model. So then once we have this, once we need to update the parameters within the random effects, we're doing that one level of random effects at a time. So we kind of fix all random effects apart a single one, and we update parameters within within random level once at a time. Also, like here, we have the visualization of what exactly parameters we need to condition on when I'm doing these updates. And after we have done this cycle of updating these blocks of parameters, we basically move to step 1 and repeat it again and again and again. Well, ideally until infinity, and practice until we are kind of happy with the properties of model convergence. Of course. Yeah. So here, like in the duck, there are two types of dependencies. So one type of dependencies is stochastic, and that's actually a part of stochastic model. So I mean, knowing rho and v and gamma and t and c, we can write this a statistical model for beta. So I mean, like Hmsc contains a statistical model for beta. But then, like this fixed effect part of latent predictor, for example, it's not stochastically dependent on anything. It's just a product of X matrix and beta matrix. So then we use the dashed lines according to this common notation of the ducks in statistical science. Okay, so well, I would say the reason why it's called hierarchical is that, like, we have, for example, beta parameters, and for beta parameters we have another level of regression based on traits, and that's one type of hierarchy in Hmsc model. The other type of why it's hierarchical is due to the potential way of how we can define random levels. So we can have random levels at the level of logs, and then random levels at the random effects at the level of sites. So then in these terms, they're going to be a hierarchy between sites and logs, because we have logs within sites. So it has both to do with the kind of model structure and with sampling design, as kind of it's double hierarchical in some sense. Okay, so then there is some extra what we call slightly more advanced Gibbs sampling in Hmsc implemented, where we can update blocks of these parameters together. And as I mentioned previously, with with the bivariate case, when we can update parameters together, it's beneficial because it reduces the autocorrelation in MCMC, but at the same time, it increases the complexity of the update. So just updating beta and updating lambda, it's like separately, but if we calculate the total kind of amount of computations we need for that, it's going to be less than updating them jointly, even if we can derive some nice way to do it. And it turned out that, like, we can do that, and we have implemented some of these joint updaters into Hmsc. There are still some of them which are kind of should be implemented further, But ultimately, there is some trade-off between whether what you gain by reducing the autocorrelation and what you lose by increasing the complexity of certain steps of Gibbs cycle. And therefore, such like trade-off probably is quite problem specific. So it very much depends on model structure and data which you feed to the model. So we kind of derived some rule of thumb ideas about what are the beneficial and what are not beneficial joint updaters, and put them as kind of I mean, by default, when you just call fit my model in Hmsc using sample MCMC, it's taken our information about what is beneficial here into account. So maybe you don't need to worry about that too much. Although if you're kind of interested and you kind of know what you're doing, you are very welcome to kind of experiment with this setting and learning of what combinations of these joint updaters are good for particular models. Okay, so now we are going slowly moving towards the from conceptual representation of Hmsc towards the practical implementation of Hmsc in code. And first, we will start with how we can adjust the properties of Gibbs sampling in Hmsc in the code. And as you already probably know from those exercises which you have been doing, that the model fits in Hmsc run using the so-called sample MCMC function. And here is the signature of this function. So here is this interface and this default values of the parameters in this signature. And we're gonna go one by one through these parameters, and I will give a brief explanation of what these different parameters refer to. So first of all, we have the model object itself. So once we are calling, when we are calling sample MCMC, we need to specify what Hmsc model we would like to calculate the posterior for. Then the next parameter is the number of samples which we would like to acquire from each MCMC chain, and what is the transient which we would like, how many Gibbs cycles we would like to discard before we will start recording these samples. Then the third parameter is thinning, and that is about how much of gap we would make between recorded samples. So how many more cycles of Gibbs updater of Gibbs, how many more cycles we're going to run compared to the amount of samples we're going to record. Then there is some argument which enables you to define some, to have control over where from these individual chains start from, and then some control over the how much of output this function prints. Okay, then we have like important parameters which are about the amount of chains we're going to have in the fitted model and how many independent processes we're going to run for these chains, as well as what type of parallelization we are asking R to use. Then we have some more technical parameters. So like sometimes, especially when you're dealing with large data, and you are kind of repeatedly fitting similar type of models, similar type of Hmsc models, it's beneficial to do the steps which Hmsc doing before it actually starts the MCMC just once and kind of record what's the output it produces. So here, like you can specify an output of another Hmsc model which has already been fitted, And then you can grab this object in order to simplify this pre-processing, which is Hmsc is doing before it actually starts doing the Monte Carlo Markov chain. As I mentioned, we have update argument updater, which gives you control over which conditional updaters Hmsc sampling algorithm is using. So technically, by playing with this, you can actually destroy the integrity of your sampler, which if you give sampler, if you completely, for example, disable updaters related to some variable. So unless you are doing that surely, and you're doing it for purpose, maybe for testing purpose, you maybe don't want to play with this too much. And then there are some other parameters. So like whether we would like to sample not from the posterior, but just like from the prior associated with the defined model, and whether to align the posterior or align the samples as best as possible according to some heuristic which we have developed in order for them to be more consistent across the chains. Okay. Yeah, please go on. Well, also, why do we want to sample from the prior? I never did that, but sometimes it's useful to visualize, for example, how wider your prior is compared to your fitted model. So kind of by sampling from the prior, it's by sampling from the prior, it's better to, you can sometimes visualize, sometimes explicitly visualize what are your prior assumptions, some properties of that prior assumptions you can visualize. Sorry, can you repeat? So as I started with, like posterior is a product of prior and likelihood normalized by the integral of those. So in this case, we are basically removing the likelihood from, like any likelihood from the model. So yes, it kind of corresponds to like we have no data though. Any other reasons?
Yeah, so I think that one reason why you want to sample from the prior is exactly this, that it's easier to comprehend what is the prior distribution by looking at it. And that's exemplified in the book where there's about like 20 pages of text about prior distributions where we try to tell what these default priors are and what they mean. And some of the priors are very easy to understand, like what is the prior for the row parameter? Half of the mass goes to 0, half of the mass is uniformly so 0 to 1. But then what is the prior for the omega matrix? That's a much more tricky thing to understand just by looking at those equations of these multiplicative gamma shrinkage prior and thinking what are the hyperprior parameters. It's too, I cannot understand what is the prior if I just look at those parameters. What I want to do is to sample and see what kind of association matrices that produces that prior, and change those hyperparameters and look at the new kind of a distribution of association matrices that it generates. It makes it much easier to understand what you are actually controlling by those prior parameters. So this is one use, and I think that would be maybe the main use for the user. And then also when you see the prior distribution in that way, you can visualize it, you can compare the posterior to that. Okay. But then the other reason why I think it's useful to sample from the prior when we are developing like the approach, and especially when we are developing, and especially when Gleb has been developing these skip sampling approaches, is that there is a lot of code. It's easy to make mistakes. Is our code correct? Are our updaters correctly implemented? That's very difficult to test because you never know the true answer, like what the posterior should exactly be, except in some simple cases. But you can use the same updaters to sample the prior, because you can declare that all data are missing. And now you fit the model, it should return the prior. And now you can compare the posterior to that posterior that should be the prior to the prior that you have sampled directly. And if they look the same, great. If they don't, you know that you have some bug, and then you can look for the bug.
Yeah, thank you. Thank you for the extra comments on this topic. And well, my last slide. Oh, yeah. I think
I
also
did
was
open my microphone to Zoom. So I think what I said went to Zoom as well, and so it will go to the YouTube as well.
Okay, so finally, like the priors in HMSC, which already been a bit touched by the question which was raised. And again, we can focus on this HMSC directed acyclic graph, and the parameters which it has, they are like of two types. Some of them are sources in the graph, and some of them are kind of intermediate nodes. So for intermediate nodes, like these are like three of them, so beta, eta, and lambda, we don't have any, I mean, like the prior for them is defined given another parameters of the model. So there is no customization which can be done beyond that. However, for the source parameters, the parameters which are sources in the graph, they are so-called hyperparameters of their priors. So all of them are assigned some priors, and these priors are given hyperparameters which can govern the like the prior distribution of this blue lighted source nodes of DAC. So regarding of these source nodes, they are like seven of them here. So 4 of them correspond to the like whole HMSC model at once, and those are like the priors for the V, which describe the tolerance to stochastic variation in species niches. Then priors for the rho, which describes the a priori structure of phylogenetic strength, a priori assumption about phylogenetic strength. Priors for the gamma, well, and then priors for residual variations. Those last two, they are less directly maybe interpretable, and like it's also less likely that you're gonna need to change those if you ever need to change any parameters, any hyperparameters compared to the default values in HMSC. And then regarding the priors, the second type of priors, those are defined for each random level separately. So those cover the spatial covariance length scales, alpha. And this is probably the most commonly necessary to adjust parameter, especially if you're doing some spatial studies, and if you need to kind of account for spatial dependence both on very small levels, on a small scale, and very large scale. Then there are like parameters corresponding to the local shrinkage of latent loading and progressive shrinkage of latent loading, which together make up the so-called multiplicative gamma process shrinkage prior, which is the prior for the lambdas, for the latent loadings themselves. So while local shrinkage is something which is quite unrecommended to play with, the progressive shrinkage governs quite often governs how many latent factors I'm going to have in the model. And by kind of increasing or decreasing these parameters, you're going to have either a smaller number of factors or larger number of factors. So how do we set up the priors in practice in code? So here are the two functions which are responsible for that. So two methods of HMSC. One of them operates over the HMSC model, and it takes the values of this, well, all these priors which I listed here, well, as well as other priors corresponding to reduced rank regression, which is a topic I'm also going to be covering tomorrow. And then for the random effects, we also have the same function set priors, which takes now not the HMSC model, but random level. And it takes all these hyperparameters listed in the slide, this second part of the slide. Well, just to sum up, so there are full flexibility on how to adjust hyperparameters in HMSC, but unless you are well familiar with HMSC, you are really advised maybe not to go to that before trying HMSC, but I mean before getting more familiar with HMSC itself and using the so-called default hyperparameters, which we have been tried to kind of acquire in such a way so that they are, well, they pretend to be applicable to large variety of practical models, practical analysis. Well, then if you're kind of specifically doing with spatial models, then maybe you would need to learn this particular one. Otherwise, these three, like the tolerance to static variation, phylogenic strength, and prior for that, as well as progressive shrinkage on length loneliness, will be the ones which you would sometimes maybe need. And this is the end of my lecture. And once we have maybe a few questions, if they are, we can have a short practical demonstration on how to do this in code. Yeah, please go on. You mean conceptual or like technical? So, like we have four source parameters defined on the for the whole model, and then three parameters defined for each random level effect. Sorry, random effect level. So let's go first through the ones defined for the whole model. So we have the parameter V, which is a matrix of covariation between species niches. So as prior for that, we can say that it's either very flexible or it's very restrictive. So as if we say that like it's very restrictive, we're kind of effective saying that we expect that all species in communities, they have their responses, their species niches, they are very, very much described by the traits only. So there is no more variation on the traits apart of what is explained by the traits. On the other extreme, we're saying that like, okay, we are basically treating our species as effectively independent. Then like the phylogenetic strength, that is a parameter specific to models where phylogeny is included. And that governs how much certainty do think that how much belief we have, for example, in that there is any signal of phylogeny in the data a priori. So as I said, like unless you kind of know that for your given example, the default prior is not so good, or kind of it's not applicable, it's maybe unrecommended to go and kind of start changing those straight away. And similarly, it's a bit difficult for me to give an example without sticking to particular study. Also, maybe you have anything on this one. Do you have a good example where we actually needed to put phylogenic strength significantly different from what is default prior?
No, I don't think I'm
Okay, well, negative answer from Otso. Yeah. Well, for example, the shape of this prior distribution. So like for example, particularly in phylogenetic strength signal, in phylogenetic signal strength, like one of the key properties of this hyperparameter, I mean of this prior distribution, is how much mass we put exactly to 0. So how certain a priori we are about that there is no signal, phylogenetic signal at all. So, for example, if you are quite sure somehow, like it's somehow quite sure, okay, maybe if you want to be very conservative about the test, that about testing whether there is any signal, any phylogenetic signal in your data, you would need to put more point mass to 0, exactly 0, because that's going to be what is going to be propagating to your posterior once you like feed the model, get posterior. And so like, yeah, like it's kind of extreme case. Imagine like we don't have any data and we use the default prior, then it says exactly half of the probability mass is at 0, but another half is not at 0. So a priori we think that, okay, we have 50-50 between having phylogenetic signal versus not having phylogenetic signal, even before we see any data. And this is maybe not sufficient if you are quite conservative and you don't want to see some small signals, so some really small phylogenetic signals. Okay, there was a question in the chat about, is it possible to modify a prior only for the beta covariates? So whether you want to add sampling effort as a covariate, not using a log link, so not offset, and want it to be strictly positive. Well, conceptually, this is possible, but it requires some untrivial play with prior for the gamma and prior for the V. So effectively, what you would need would be to identify those elements which correspond to this column of betas, sorry, to this row of betas, and correspondingly identify those elements in the V which would correspond to those, and manipulate with priors in such a way that like it's very narrow for this particular beta, but then it's still flexible for others, for other elements in beta. So like currently we don't have this option to include an offset per se, but it's something which we are actually in developing, like, because exactly, I mean, I don't fully comprehend why you have called it not an offset, but it's something which we kind of going to have in quite near future, that like we have a potential offset for the linear predictor, well, basically component wise, which you could have, well, which you would be capable to define according to your liking. Okay. Yeah, of course. Imagine you are like doing some modeling of plants on some archipelago, and then you have, for example, large distances between islands, and then small distances within islands. Then you may consider two levels of spatial levels in Hmsc here. So one of them is going to be summarizing the like it's going to be devoted for the islands, while the other one is going to be devoted for the spatial structure within the islands. So in this case, the default prior for both of them is going to be just kind of like it's going to have a point mass on 0, and then it's going to be flat between the 0 and maximum distance between your units. So because maximum distance between your sample sites within the islands, I mean, between your all sites, they are pretty much the same as the distance between islands themselves. This is not going to be very well characterizing the local spatial dependency, which you can have within island. Therefore, you may need to adjust the spatial scale for that level to be something on the level of size of a single island.
So basically, if you have one level of spatial coverage, should it be necessary?
Well, unless you're kind of specifically interested in local effects. So if you're kind of more sure that like there are some global effects, you should go with maybe default prior. But if you are more interested, like, okay, there are no evidence of long range effects going on, but there can be some evidence of that there is some very fine scale dependency. And your data allows you to explore such. So you actually need this, some of your locations need to be close to each other, while some could be far away. Then you may kind of still consider this option. Okay, we have 2.5 minutes. So any ideas? Should we proceed now or should we leave this kind of with like demo for the next time?
Yeah, I think what we could do is to break here and go for the exercises of today, like with the scheduled plan, so in this couple of minutes. And you know, it's great that you went over it because you know there were questions and discussions, so I was very happy to see that. And what we could do is that you could continue by showing how you modify those priors in practice tomorrow. And also that's actually best to be done after I introduce the bird case study, which I have not done yet because I understood that you will use that for these illustrations. So let's do so that you save that R demonstration for tomorrow.
Okay, deal. Okay, then thank you for your attention, and let's proceed with the breakout rooms and keep going on exercise there.
Yeah, so we will do like we did in the earlier days, that people physically here